Hi, my name is John-Michael Colef, and I'll be doing problem 2 of homework 2 for probability and stochastic processes. Okay, so problem 2, part A, asks us to draw the probability distribution function, capital F of x, which is this. Now, before we start, let's just remember, what does e to the minus alpha x look like? Let's say that alpha is 1 for now. Let's say e to the minus x. What does that look like? So e to the minus x looks something like this. It's a decaying exponential. Here, as x approaches infinity, this asymptotically approaches 0. Now, minus e to the minus x is just this function, but flipped over the x-axis. So it looks something like this. Asymptotically approaching 0 as x approaches infinity. So that's minus e to the minus x. But now we're adding 1 to it. So adding 1 to it just basically shifts it up by 1. So it's going to look something like that. Whoops. It's going to look something like this. And now, instead of asymptotically approaching 0 as it did here, because we shifted it up by 1, it's going to asymptotically approach 1. So it'll look something like this. Great. So we got this part, the 1 minus e to the minus x. However, we have this step function. So the step function is defined that whenever the argument inside is less than 0, the step function is 0. Whenever the argument inside the step function is greater than or equal to 0, whenever this argument is greater than or equal to 0, this becomes 1. So I'm assuming that C is a point that's greater than 0 because we can't have negative probabilities. So I'm going to say that C is somewhere over here. I'm just going to label it in black so we have C. So because the step function is 0 anywhere before C, we don't have any part of the exponential before C. It goes away because this part times 0 is just 0. And then everything from C and forward, it's just this because it's basically this times 1. So what this ends up looking like in the end is we have a jump here at C, and then we have this exponential asymptotically approaching 1. This point here is just this piece at x equals c. So we have 1 minus e to the minus alpha c. That's what this point here is. And that is what the probability distribution function f of x looks like. Okay. Part B. We are asked to find the probability density function, which is little f of x. And that equals the derivative of the probability distribution function, capital F of x, with respect to x. So I'm just going to use product rule for this times this. So we take the derivative of the first part, which will become alpha e to the minus alpha x times the second piece, u of x minus c. That's an x. And we add it to the derivative of u of x minus c with respect to x, and multiply by this 1 minus e to the minus alpha x. Okay. So we're asked to draw what this looks like. So let's just simplify this a little bit. This part stays the same. We have alpha e to the minus alpha x, u of x minus c, plus the derivative of the step function is just the delta function. We multiply by 1 minus e to the negative alpha x. Okay, so let's draw this piece by piece. Let's first draw this part. So here we have alpha times e to the minus alpha x. So here we have our axes. So I'm going to assume, by the way, that this point up here is alpha. So this exponential, let me just draw it in black so it's easier to see. So we have our axis. we have the point alpha right here. So e to the minus x is going to look something like this. But because we're multiplying by the step function, again, all we care about are the points after x equals c, which is right here. So all we care about are the points here. Everything else gets annihilated because the step function is 0. So far, we have here a jump at c and this exponential decrease. So as x goes to infinity, this goes to 0. This point here is just this piece at x equals c. So here we have alpha e to the minus alpha c. That's this point here. I'm just drawing a little arrow there. Now we're going to add the delta function times this piece right here. Well, the property of delta function is if I multiply the delta function by another function, it's just going to be the function evaluated at the place where the argument of delta function is 0. Why is that? So the delta function is 0 everywhere except for the point where its argument equals 0. So the argument equals 0 at x equals c. The argument, that's when the argument equals 0. That's when the delta function is equal to 1. So what's going to happen is we're going to have a delta function at x equals c, and the magnitude is going to be 1 minus e to the minus alpha c. And because it's going to be 0 except when x equals c. And then we still have this piece over here. So this is just going to be a delta function here with magnitude 1 minus e to the minus alpha c. So we add that delta function to what we had originally. And this is the probability density function, little f of x. Now, we're not done. Part B asks us now to discern whether or not this is a valid probability density function. So for this to be a valid probability density function, it must satisfy the following condition. And that condition is that the integral from negative infinity to infinity of the probability density function is equal to 1. So we'll do that. We'll check. So we want the integral from negative infinity to infinity of alpha e to the minus alpha x. I'm just going to put a bracket here. U of x minus c plus delta x minus c times 1 minus e to the negative alpha c. And we have our bracket here. And all this is integrated from negative infinity to infinity. And we want to check to see if it equals 1. So I put a question mark here because I'm not sure if it equals 1 yet. I'm going to check. So we can separate this piece into two integrals. This integral of this from negative infinity to infinity plus the integral of this from negative infinity to infinity. So let's do that. I have my first integral, negative infinity to infinity, of alpha e to the minus alpha x u of x minus c dx plus the integral from negative infinity to infinity of delta x minus c times 1 minus e to the minus alpha c dx. And we're checking to see if it equals 1. Here, because we have the step function, everything before x equals c is 0. So anything from negative infinity to x equals c, we just get 0. So it's basically like we're integrating from c to infinity. So we can write this integral as the integral from c to infinity, because the delta function kills everything before c. So it's the integral of from c to infinity of alpha e to the minus alpha x dx. Now this integral is even easier because we have a delta function. The integral of a delta function times another function is just the function evaluated at the point where the argument of delta function equals 0. Because the delta function equals 0 everywhere except where its argument equals 0. So in this case, it's when x equals c. So this delta function is 0 everywhere except when x equals c. When x equals c, the integral of the delta is just 1. And 1 times this. So all we're going to get is just 1 minus e to the minus alpha c. So all we have left is to evaluate this integral. So we can pull out alpha because it's just a constant. The integral of e to the minus alpha x is just 1 over minus alpha x, which I'm just going to pull out the minus alpha x. And we have e to the minus alpha x evaluated from c to infinity. And we have this, whatever is left here on this side. So this just becomes minus 1. The e to the minus alpha x evaluated as x approaches infinity is just going to become 0. So we have 0 minus e to the minus alpha x at c. So e to the minus alpha c plus 1 minus e to the minus alpha c. If I distribute the minus sign, I get e to the minus alpha c plus 1 minus e to the minus alpha c. This e to the minus alpha c cancels with the minus e to the minus alpha c, and we get 1 equals 1. So this indeed is a valid probability density function, and that completes the problem.